last night's dinner. We're standing with Valerie. And then we'll see. Hopefully, maybe more people will be coming as you go on. But I guess we'll have to start now. Please.
Yeah. Okay, I'm just going to start with the most interesting part, and then everybody who comes late, tough luck, right? So I'm proud of everybody who made it. I struggled this morning. Okay, so just briefly, where do we stand? So we talked about inflation yesterday, and we'll be continuing to talk about inflation today. So yesterday we talked about background evolution, in particular the evolution of the scalar field, which is governed by the slow roll equation of motion here. We talked about the slow roll conditions, that epsilon and eta should be much smaller than 1 so that we can work in this approximation where the Hubble parameter is constant, the equation of state is approximately -1, and the scale factor grows exponentially with time. And then we also, at the very end of the last lecture, we already very briefly touched on perturbations. And particularly we saw that if we're looking at the scalar perturbations, which are contained in this scalar field, which is called the inflaton field, and in the metric, then we have one dynamical or physical degree of freedom, which we can express in a gauge invariant way in terms of this curvature perturbation here, which contains a term from the metric and a term from the scalar field. And what we want to do today is now really dive into these perturbations and see what sort of perturbations inflation predicts and how we can compare those to observables in the CMB. And I was serious that we're going to start with the most interesting part because I'm going to draw a sketch which will explain to you all the physics, right? And then we go through the calculation. So people who just come for the calculation and not for the picture, tough luck. Okay, so what I want to draw here is co-moving scales on this axis. So in particular, this will be k, so the co-moving wavelength of any given perturbation mode. Because we'll be working entirely in linear theory, I can always go to Fourier space, and I can do analyze by problem k mode by k mode. So this will be an important quantity. And we will also be looking at the co-moving Hubble horizon, ah to -1. And all this is a function of time, tau. Okay, so the co-moving k mode, by definition, so the co-moving length of any perturbation, since it's co-moving, it's just going to be a constant. So this is k to the -1. The interesting thing is, what does the Hubble horizon do? The Hubble horizon, co-moving Hubble horizon, during inflation, it will decrease as we saw this relation here, the relation between tau and h, right? Because we have that ah to the -1 is equal to minus tau. So we just have a linear decrease in this log plot. And then after inflation, so all this is inflation, and then after this, it will grow again as something proportional to tau, depending on if we're looking at matter domination or radiation domination. So here we have matter or radiation domination. And the two important points in this plot now are this point and this point. Because what happens here is that we start here on the very left. We start with a perturbation mode, which is small, right? That's how we expect. We generate a thermal fluctuation, something like that, right? Or a quantum fluctuation. It should be on kind of small scales compared to the Hubble horizon. Hubble horizon is a big quantity for particle physics. So we start with a small perturbation. But then, simply due to this evolution of the Hubble horizon during inflation, this small perturbation will exit the horizon at this point. So this is what we call the horizon exit. And then over here, then they will just stay outside the horizon for a long time, potentially. And then at some point, universe becomes matter radiation dominated, and hence the Hubble horizon, or the inverse of the Hubble, the Hubble horizon starts increasing again, and hence over here we will at some point get to the point where we have horizon re-entry. So what we'll be talking about today is the left-hand side of this plot, basically up until this point. So how these fluctuations are generated during inflation at small scales, how they get pushed outside the horizon, and how they behave then once they are outside the horizon. Now, what you probably did with Fabio is basically everything to the right of this dashed line, because then you have these super horizon fluctuations, the scalar power spectrum and the tensor power spectrum, and then when they re-enter at exactly this point here, this is the point when these fluctuations then become again dynamical, become subhorizon, and they leave their imprint on the plasma of the early universe. And in particular, if we look at fluctuation modes, which re-enter at exactly the time when the CMB decouples. So different modes, right? I can draw different modes here. Here could be another mode, right, of different wavelength. But there will be one mode, or a set of modes, which will re-enter the horizon just around CMB decoupling. And they will imprint the perturbations of the CMB. So if we want to understand the predictions for these modes, we have to go back all the way back along this line. So say this is a CMB re-entry, right, or CMB decoupling. Then we have to go back. We identify the wavelength. We go back all the way here. And then we need to see what's going on in inflation at exactly this point in time, which will be roughly 60 e-folds before the end of inflation, and understand the predictions for the fluctuation modes at that point. So concretely, what the strategy is going to be is we're going to expand, in order to compute these perturbations, we're going to start with the action for our scalar field. We have to expand everything out to second order in the action, so that then we can get the equations of motion to first order the perturbations. And then we need to quantize the system, because we want to understand quantum fluctuations as the origin of the CMB perturbations. We need initial conditions in order to solve our equation of motion. And then we just solve the equation of motion, and we obtain a solution, and that solution will then give us the predictions, and in particular the power spectrum for those fluctuation modes, which then are directly imprinted into the CMB. So that's the strategy, that's the idea. Before I go into the actual computations, are there any questions so far? Okay, one person awake.
Thank you very much. That scale that we enters at the CMB, but this will be then the largest scale in the CMB, because in the CMB that you have also all the small scales in the BAO.
Right, but in the terms of, I mean, in principle, we look at all of them, right? We look at all the scales that we can observe in the CMB. But still on kind of a plot like this, right? The CMB is still only basically one scale, or one characteristic scale. Because we're talking about, I mean, if you think about how much the scales vary in the CMB, right? I mean, you have like maybe an order of magnitude. But inflation here is 60 e-folds, so e to the 60. Right, so then it covers a lot more scales than we can measure with the CMB.
Yeah. Okay. Thank you very much.
Any other question?
Okay. So then let's get to the first point. We compute the action to second order, the perfect thing to do on a Friday morning after the conference dinner. So we will, I told you yesterday, right, that you can either take gauge invariant variables, or you can make a gauge choice. In this case, we're going to do the simpler solution, right, because also we can look in a textbook and we know the results, so we can be more confident that we're doing it right. And so we're going to do a gauge choice. So we're going to gauge choice. So we're going to set del phi is 0. And that means that in the metric, so here, I would normally have the Newtonian potential psi, but now I already want to just express this in terms of r, right? Because if I said delta phi equals 0, right, then this curly r, the curvature, is just psi. But since in the end we want to actually write things in terms of this curly r, let me just write it in terms of this, but you could also just write the psi and compute with that. And then we have the tensor mode, which we will not be worried about in this lecture. So we want to compute everything to second order in this parameter, and then we want to, in the end, compute the power spectrum for this parameter, for this perturbation. Okay, so you start with the action, right? So yeah, the one we had on the board the other day. So we have the part of the scalar field, and we have the Einstein-Hilbert action, and then you have to expand everything to second order, which is one of these computations. It's not really difficult. It's just kind of long, and it's one of these computations which get very, very long in the middle, and then very nice and short at the end. And if you lose one minus sign on the way, it doesn't go back small, right? So I'm not going to go through all the steps here because I don't think there's anything interesting in the individual steps, but they are in all glorious detail in the TASI lecture notes by Daniel Baumann, if you want to look them up. But anyway, the result after some computation, and once you see the result, you can kind of say, okay, well, you could have nearly guessed it. So a to the 3 phi dot, well, nearly guessed it, not quite. Phi dot squared over h squared, r dot squared minus a to the minus 2 del I r. Okay, so basically this is more or less a box operator, but with some factors of phi dot over h, which take into account that there was also the scalar field and the expansion of the universe in the game. Okay, so now let us simplify that. To do that, let me introduce, to write this prefactor in a bit more compact way, I will introduce z as a phi dot over h, right? Basically this prefactor. Can you actually see this dot? Maybe, okay, tiny dot here. Okay, we'll write in terms of this. I'm also going to now introduce conformal time. So I write d tau instead of dt, which means I get an additional factor a from the volume integral, which then makes this thing a to the 4. And then I can take out, for the first term, this is just z squared, right, with an extra factor a squared. So I get a squared, z squared, r dot squared. And then for the second part, I just directly have, if I combine this, z square, right, because you have a to the 3, a to the minus 2, and then 2 a's go into the z, so z squared. And the gradient. Okay, now we want to canonically normalize our thing, right? So now we kind of see, okay, this is starting to really look like a box operator. Not quite, because we have all these prefactors. So let's try and canonically normalize our variable. So this thing, so we're going to introduce now v, so-called Mukhanov variable, which is defined as z times r. So the idea is to absorb these factors here. And now that means that we can rewrite this guy as v prime, so where dots are d over dt and primes are d over d tau, minus z prime r squared. Right, so what's basically happening here is that I'm acting with a time derivative on v, which means I get I do chain rule, I get a time derivative on z and a time derivative on r. But here I just want a time derivative on r and not on z. right? So then I need to subtract the other term. Okay, and this one is easy. This is just the gradient acting on V, because recall that this Z depends on time, but not on space, right? So here the gradient just acts on V. Okay, and with that, we can simplify this into d tau d3x V prime squared minus, so this is from up front, this is the last term, and now we have the mixed term and the squared term here. So minus 2v prime v z prime over z. I'm trying to get rid of all of the r's, right? Because I want to replace all of the r's with v's. Minus v z prime over z squared. And then you can see that this term, this is already, starting to look like part of a square, right? So if I can write part of a total derivative, I can write this as minus d over d tau z prime over z v squared plus v squared z double prime over z, right? I mean, to see this, just act with the derivative here, do the chain rule, right? And you'll see you'll reproduce exactly this term up here, apart from the double derivative on z, which corresponding you have to subtract here. But now, since we're in an integral, right, we're just going to do partial integration, meaning we just drop this total derivative. And then what we're left with is 1/2 d tau d3x v prime squared, the gradient, plus z double prime over z v squared. So we have some variable, right, which is now canonically normalized. Here in front, it just has the usual kinetic and gradient term. And there's two non-trivial parts. So when I said you could have nearly guessed the result, right? I mean, I think this first part you could have guessed. So the somewhat non-trivial thing is that here you have something which looks like a mass term, right? But with a time-dependent mass, so the mass given by z double prime divided by z. And the other thing, which I think is a bit non-trivial, is to get the normalization right? So to know how this canonical variable actually relates to the variable that we're interested in, which is this r, right? Which is of course important if we want to get the normalization of the power spectrum right at the end. Yes? The gradient, right? Here. No. Yes. Here's a minus. Wait. So where are you? That one?
No, up there. Yes, just above. No, just below. In between. So on the rightmost. Is that a minus or a plus for that term? I say it's a plus.
Because it comes from here, right? It's when it's the square term here. So I think it should be plus. And then does that make that correct here? It's fine, okay, but I need to put a plus here, right? And now I'm also thinking that this should be a minus, right? Because it's a minus in the line before. Okay, so now we have the action, the second order in our perturbation. Now we can do Euler-Lagrange to get the equation of motion. And we're going to make our life a little bit easier, since this is a linear theory. I can always go to Fourier space, in which case the gradient just becomes a factor k squared. And we don't have to worry about this. Then we really just have an ODE in time. So we do a Fourier expansion so v of tau and x is d3k 2 pi cubed Fourier coefficient Vk of tau e to the I k x. And then we just take the action here. We do Euler-Lagrange. And okay, we get to the double prime, so 2 time derivatives, and then we get the k squared. So this part is just the usual box operator in Fourier space, and then we get the mass term, so minus z prime over z. Okay, so this is exactly the same equation of motion you would get, just if you had a massive scalar field with the mass term z double prime over z. And this is an important equation. I'm not going to risk, well, maybe I can put a box on it, even though I cannot see where I'm drawing. Okay, good. This is, let me call this M for Mukhanov equation. This equation has two important limits. So one is if k is much, much larger than AH, so large k, small scales. So this is the subhorizon limit. Then this just describes free oscillations, right? Because then we can, then if we recall again, so Z was defined as A phi dot over H. So you can now actually compute Z double prime over Z. And if you use roll approximation, can do this as an exercise, it's about one line. Then you get here to roughly, you get 2A squared H squared in the roll approximation, meaning that k much larger than AH means that we can drop this effective mass term here and we just recover free oscillation. And in the opposite limit, which is the superhorizon limit, this Z double prime over Z is important and actually dominates over the k square. And if you recall back to the previous slide, just very briefly here, this is exactly depending. So sub or super horizon, k larger or smaller than AH is exactly the question: is k above or beneath the Hubble scale? Okay, so now we've done the first step. We have derived an equation of motion for our scalar perturbations, valid during inflation, valid in the slower approximation. Any questions so far?
We're still waking up.
Good.
Well, I do have myself.
No minus signs, please.
No, it's a bit more conceptual. Actually, it's my bad memory. You said that you could replace the psi in the spatial part, the diagonal part of the metric, by 2r, where r is the curvature perturbation. Could you elaborate a bit on that? Because I forgot.
So it's basically here the definition of r, right?
So this is the gauge invariant.
Yeah, this is the gauge invariant r, right? So if I was doing everything in the perfect, most careful way, I would keep both this fluctuation and this fluctuation, and then work really hard in order to express all my results in this gauge invariant way. Now, instead, what I'm going to do is I'm going to do a gauge choice. And the gauge choice that I can do in this case is to take just delta phi to 0, in which case I'm basically just doing the power spectrum of this guy, the psi.
Is that the conformal Newtonian gauge? No.
I think so, but since this is being recorded, let me
Okay, no worries.
let me be careful, right? But then, at the end of the day, since I know that this R is gauge invariant, right? I can compute this R in any gauge, right? And I know that the final result has to match in whatever gauge I do it, as long as I compute all the way to an observable, right? The intermediate steps may be dubious, right? Because I've made a gauge choice. The intermediate things can be gauge dependent, but at the end of the day, we want to compute temperature perturbations in the same B. That's an observable, right? And hence we take the shortcut and just drop this guy.
So then you just drop the guy and then equated R with psi. And that's what you did.
That's what I did.
Okay.
And the factor 2 is just the way it's defined in the way the Newtonian potential is defined.
Thank you.
Any other questions? Okay. So then the next step in our strategy was that we have an equation of motion now, right? But we need initial conditions to solve this equation of motion, and we still need to quantize our system. The reason I need to quantize my system is that yesterday we just assumed we have some classical, perfectly homogeneous field, right? And that gives us the right conditions for inflation at the level of the background. But we live in a quantum universe, right? So even if by hand I assume or I put a classical field which is perfectly homogeneous, which I can do, and also even if it's a bit, we discussed with some of you in a coffee break a bit yesterday, even if it's slightly inhomogeneous or even significantly inhomogeneous at the beginning, inflation will kind of stretch everything, so it will make it more homogeneous. But that's all true at the classical level. We will always have quantum fluctuations. That's kind of unless we somehow get rid of quantum mechanics at those high scales, that's kind of really a definite prediction of inflation or a definite prediction of how we understand quantum field theory. Even if we put a classical homogeneous field, there will be quantum fluctuations, and these quantum fluctuations will generate precisely these perturbations, and these perturbations will then leave an imprint. So we need to compute them, which means that we will promote our V variable to a V operator, which is very simple if you do this as physicists do this, because you basically just write down, again, the Fourier expansion, and you just add an operator, right? So we have the Fourier coefficient, which depends on time. We have an operator, an elation operator, A, e to the I kx, and then the complex conjugate. So notice that for these Fourier coefficients, I'm dropping the k vector. The reason, already here I dropped the k vector in this equation of motion. The reason is that the equation of motion only depends on the absolute value of k. So all fluctuations for a given absolute value of k will behave the same independent of the direction, so that simplifies my life a bit. Okay, then here we have the creation operator and e to the minus kx. Okay. And now we impose the usual canonical quantization conditions, which means we impose that a k commutator with a k prime is 2 pi cubed delta k minus k prime. And the commutator of v, x and tau, together with its conjugate momentum, so let me hold up pi v, what's an operator of, y and tau, is I delta x minus y. Now, if you can, v we've given there, right? Pi is just the conjugate momenta, so you can get it by taking derivative of v. You plug that inside this commutator. You use this relation here for the a and the a dagger, and then you get from that you get a relation between the Fourier coefficients. So you get that I h bar is vk star vk prime minus vk prime star vk equal 1. So this is the relation that the Fourier coefficients need to satisfy in order. So I skipped 2 or 3 lines there, right? But conceptually, what you do is you take this guy, you take the derivative with respect to conformal time, you plug it in here, you evaluate these things, you end up with these types of projects, you plug in this, right? And then you say, okay, you need to get this delta on the right-hand side, and the only way you can get this delta is by having this relation among the Fourier coefficients. And this is the relation that the Fourier coefficients need to satisfy in order to have canonical commutation relations for our scalar fields. This is something which one does in quantum mechanics all the time, right? We just kind of forget about it a bit when we do then cosmology. But this is the relation we need. Then the other thing that we need to think about is initial conditions. And as you saw in this plot, right? Initial conditions mean we go here all the way to the left, and all the way for any given K mode, if we go far enough to the left, the mode will always be far subhorizon, right? Which means we can always go into this equation in the limit that the K dominates. You can't see if I point to my screen, right? So we go to this equation in the limit where the K dominates. And we can do that for every mode as long as we go far enough in the past. So in the far past, we always have K larger than AH. So that means that our Mukhanov equation just becomes Vk double prime plus K squared Vk equals 0, which is just harmonic oscillator. Okay, and harmonic oscillator is, I think, the only system in physics that we actually know how to solve, which is good because all of physics is just harmonic oscillators. So the harmonic oscillator has a unique state which minimizes its energy. So in the limit of past infinity, so tau goes to minus infinity, this Vk should really match the minimum mode in the harmonic oscillator, which is e to the minus ik tau divided by square root of 2k. Okay, so the normalization square root of 2k is just the usual normalization from the harmonic oscillator. Now, normally in a harmonic oscillator, you can have two modes. You can have negative frequency modes and positive frequency modes. Here, we only have the positive frequency modes, and the reason for that is that this condition here kills the negative frequency modes. So I've already used that. So let me call this star, right? And here I already used this, so only positive frequency modes to star. And that means at this point we have our initial conditions fully fixed. Okay, because we had the one is the quantization condition, the other one is that in the infinite past we really need to follow the harmonic oscillator equation, which we know how to solve. So now we can go back to our Mukhanov equations with initial conditions that we know and simply solve the equation of motion. So we solve the Mukhanov equations in the zeta limit, so really in the limit omega is -1, h is constant. Okay, so then in that case, right, we know that tau is -1 over AH, which means that this we can again evaluate this z double prime over z, right? Actually, this is the same as I already told you the answer, right? So if you evaluate z double prime over z, right? Told you up here, right, that this gives 2a squared h squared, which is the same as 1 over tau squared. So we get vk double prime plus k squared minus 2 over tau squared. Vk is 0. And then we can just solve this equation with these initial conditions, and the answer that you get is that Vk is e to the minus ik tau divided by square root of 2k, 1 minus I over k tau. Important equation gets 2 stars. Okay, so this is the solution for our scalar perturbations as a function of time, a solution for the Fourier coefficients. You can now think again about those two limits, right? I told you we have the superhorizon and the subhorizon limit. The subhorizon limit we already talked about, right? So then we just get the harmonic oscillator. Now, since we have the solution, and the solution is valid both superhorizon and subhorizon, right? Because we solved the actual Mukhanov equation. So let's have a brief look at the superhorizon limit to see what happens with the solution. Right, so this means that k over AH, which is minus k times tau, is much smaller than 1. And then also recall that the variable that we actually want to solve for, right, the curvature perturbation, is proportional to V over A, right? This is just the way we had defined it. And that means that if we, let's skip one step. Back here. Okay, so if we just now go to the superhorizon limit, this Vk double prime minus 2 tau squared over Vk is 0, right? So now we just drop the k squared in this limit. This you can very easily solve, right? The solution to this is simply that Vk, just the differential equation, is A tau squared plus B over tau. Can just take the second derivative, right, and see that that works. This is the general solution to this equation of motion. And now we recall that this curvature perturbation is actually Vk divided by A. And A is proportional to 1 over tau, right? So that means that here we get something like minus A h tau minus bh. And now this thing here, as time, remember that tau runs from minus infinity. So A and B are just integration constants, okay? H is the Hubble parameter, which is constant. And now remember that tau runs from minus infinity at early times to 0 at late times. Late times mean late times during inflation. So as time evolves, this term gets, for whatever fixed integration constant you use, this term eventually just goes to 0. So this term decays, we say. And this term is just constant, right? So what that means is that on subhorizon scales, we have a harmonic oscillator, right? Our perturbation is oscillating as you expect with an exponential or with a cosine or something. But on superhorizon scales, it doesn't oscillate, right? The fluctuation does not fluctuate. It's once we cross the horizon, your oscillating function just becomes a constant, right? So this is really what, so if we would draw R, right, as a function of tau, you would have something which oscillates, and then once it crosses the horizon, just becomes constant. This is what Mukhanov equation is telling you. Are there any questions on that? Yes.
Yes, I have it's basically a QFT question. When you do the quantization up in the left panel, you are using this usual prescription of having the classical solution times the quantum operators of the harmonic oscillators, so on. Now, I know this works explicitly for a Klein-Gordon-like field, but should I have some different field during inflation in which doesn't have a Klein-Gordon-like equation, like for instance a field with just one time derivative in its equation?
Well, but this is, I mean, we have the equation of motion, right? The equation of motion is this. This is very much a Klein-Gordon-like equation.
No, sure, but I mean, like in general, this is prescription.
But this is general. We have not assumed anything.
But even if I had a different equation of motion for another field, I'm talking, and I wanted to quantize another field.
I mean, okay. So we're doing single field inflation here, right? But like, I've not made any assumptions, for example, on the scalar potential of that field. And also, I mean, if you have, so if you say you have multiple scalar fields, then what usually happens is, you have a complicated field space, but effectively you have one trajectory along which the field is evolving, right? Some valley. And so you can just reparameterize your field into some effective field which runs along this valley. And then this is what you call phi. And then again, you have a Klein-Gordon-like equation. So adding more fields does not change the picture. You will still get something which is Klein-Gordon-like.
Okay, I see. Thanks.
And I think you can nearly basically always describe the dynamics effectively with just a single scalar field. Because as we discussed yesterday, if you try to do anything else than a scalar field, if you try to do a vector field or something, right, you end up with an anisotropic universe. So you're kind of effectively always in this description. Any other questions?
More questions?
Okay, so now we have the solution. I think the microphone's off. But okay, so this term goes to 0?
I mean, when are you taking this limit? Are you taking it at the end of inflation, and you understand?
Yeah.
At the end of inflation. You want to see what happens at the
no,
end?
once I go super horizon.
Once
Once
you go super
once I go
horizon.
outside the horizon, right?
Mm-hmm.
But in particular, the point is that, I mean, this definitely decreases, right? I mean, even if it doesn't go all the way to 0, this decreases, right? This is constant. So eventually I'll always get to the point that the second term dominates. Okay, so then we come to the third step, which is the power spectrum. So we're gonna, so what we want to compute is the power spectrum, meaning the 2-point function of this curvature perturbation at equal time, but different, a priori different position x and x prime. And I'm just gonna call this quantity, this 2-point function, psi, here for simplicity. And then the statement is that we're gonna, we have observed in our universe, right, and we're going to assume for the purpose of this computation, we're going to assume a statistical homogeneity and isotropy, right? On small scales, our universe is obviously not isotropic, not homogeneous. This direction looks different in that direction, right? But on large scales, it is very much homogeneous and isotropic. And hence, this means that we can always express this 2-point function as a function of only the difference between x and x prime. This is homogeneity. And here, it can only depend on the absolute value, not the direction. That is isotropy. Now, in Fourier space, that same statement translates, there's a bracket missing here. It translates to the fact that I have a delta function between k and k prime. And the power spectrum, which is the thing that we want to compute now, can only depend on the absolute value of k, right? That is, again, isotropy. So this is the guy, this formalism is just to say, okay, this is the guy we want to compute now. And in practical terms, one is often interested in basically doing a momentum integral over this guy, and then one is interested in the integrand, which typically comes with this k cubed over 2 pi squared prefactor. And so this is very often, instead of computing this power spectrum, one calls this the power spectrum. And if you look at 3 different papers, they will use 4 different notations. So this is the guy we will actually be computing now. Okay, so how do we compute it? So recall that this R was V over Z. And then Z was A phi dot over H. So we have VH A phi dot. So that means that if we compute this guy, RK prime, we will get the 2 pi cube prefactor delta k plus k prime. So here I didn't put the star, right, which is about k plus k prime. If I put the star, then I have k minus k prime, right, but it's the same. Then I have H over phi dot squared. This is just the prefactor from because we've computed the equation of motion for V, right? But I want the power spectrum in R, right? So I have this H over phi dot prefactor, and then I have don't want to spoil this. So then we have VK, which is a function of tau, divided by A squared, and here there's absolute value squared. Okay, and this is the guy we've computed, right? So this, now we just plug in the solution, so the 1 over A squared just stays, Then we had the solution, right? So at 1 over square root of 2k, so that square that just gives me 1 over 2k. And then we have the absolute valued square of this guy, right? Which is just 1 plus 1 over k squared tau squared. Now I'm going to replace a with the usual h tau, and I'm going to take this k squared tau squared out front. So then I get h squared over 2k cubed. And then the second term here is just 1, and this first term here is k squared tau squared. And now the statement is that on superhorizon scales, this goes to 0 by definition, right? So superhorizon, this will go away. Remember that h is constant. So again, on superhorizon scales, the Mukhanov variable is constant. On superhorizon scales, also the scalar power spectrum for R is constant. Which means that what we need to compute is this R squared at horizon crossing. And horizon crossing, just to remind you, means k equal a star h star. So star indicates, star is my definition of horizon crossing, right? For every given mode, I can compute a time when this mode exits the horizon. That's my time t star for every k. And then all the indices with star means I have to evaluate it at the horizon crossing corresponding to that mode. So we compute it at horizon crossing, and then it remains constant. So that means that just plugging all this together, right, we get rk prime is 2 pi cubed, the delta function h star, meaning evaluate at horizon crossing, phi dot star squared h squared 2k. And this is now valid at all times from horizon crossing to the end of inflation. Okay, because we just derived that's constant, right? So this is valid. This expression for the power spectrum is valid at horizon crossing and at all later times. And that means, just now correcting for the now actually computing this delta r squared, right? Just taking into account the 2 pi and k factors. This means we get, delta r squared is h squared 2 pi squared, and then h squared again, phi dot squared. Okay, and now recall also that h and phi dot are, however, constant, approximately constant during inflation. So the prediction is at any given scale, we can compute the scalar power spectrum. It takes this value at and beyond horizon exit. But since h and phi dot are basically constant, it means we're generating, for every k, we're generating a power spectrum of the same amplitude. Okay, so we're generating a scale invariant power spectrum from inflation. So scale invariant. So that is the prediction for the scalar power spectrum from inflation. Now, let me briefly show you how that connects to observations, right? And then we'll go for any questions. So this is just okay. Again, just notation, right? So we like to parameterize things in basically the scalar power spectrum in this way. Oh. So here, this this broke a bit, right? So this is the scalar power spectrum. This is an amplitude. All of this, apologies, right, should be an exponent. So ns minus 1 is the spectral tilt of the power spectrum. Alpha is the running, and so on and so forth, right? So we basically approximate the power spectrum as a power law where ns equal to 1 would be a perfectly flat spectrum, right? Basically, the leading order prediction that we get here, scale invariant spectrum. And then these corrections indicate the corrections from this type of a power, from this flat power spectrum. So concretely, just to show you what this looks like, if we go back, so if I can now, right, so we had the expression for delta R squared, right? And I can now just plug in for, so this is this expression up here, right? It was just dependent on the Hubble parameter and phi dot. Now, phi dot I can express in terms of the first Cristóbal parameter, right, which was basically phi dot over h squared. And h itself I can express by just the scalar power spectrum. I can by the scalar potential, okay? Because h, according to the Friedmann equation, is just the scalar potential. So if I just plug that in, I will get in this lower approximation that this is v of phi divided by 24 pi squared epsilon v. And if I want to evaluate that at the CMB scales, it means I need to evaluate it at the point of time when the modes that we see in the CMB today exited the horizon during inflation. I can then also compute ns minus 1, which is, according to the definition on the previous slide, just the dln of the scalar power spectrum, dlnk. Then you rewrite that as dln delta r squared d phi over dn over dlnk. And then, okay, you can use here this. Okay, so this is the leading order in epsilon. This is just 1 because k grows exponentially in n. This guy we computed in some earlier lecture that the n is just minus 1 over 2 epsilon d phi. For this one, you have to work a little bit, but you can show that this is 1 over 2 epsilon minus 6 epsilon plus 2 eta. So when you plug all that together, you get minus 6 epsilon plus 2 eta. Where here the epsilon and the eta are basically is always the potential slower parameters. This so far is completely general. Now we can plug in our scalar potential from the previous lecture, m squared phi squared, and we can just evaluate delta r and epsilon. Okay, so delta r. What you basically see is that, okay, you get delta R will now depend on the mass. So by matching this to observations, we will be able to determine the mass of the scalar potential. The NS, because it only has V prime over V or V double prime over V, will not depend on the mass. So NS is actually a prediction independent of the mass of the scalar potential. And if you just evaluate epsilon and eta for the scalar potential, what you will get is that ns minus 1 is, well, let me write this way. So ns is 1 minus 2 over n star, where n star is the e-folds when the CMB scales exited the horizon. So if we say this is about 60, then we have a prediction for ns, which is 0.97. So this is slightly larger than the observed value. More importantly, this m squared phi squared model, when you compute not the scalar, but the tensor perturbations, it gives you a value which is larger than what we observe. But this simple model is just to show you how independently of the scalar potential, right? You can get all the way up to here, and then you plug in the scalar potential of your favorite model, and then you get concrete, really, numbers for the amplitude of your scalar power spectrum and the slope of your scalar power spectrum, and all other parameters, right? So you can fully parameterize the scalar power spectrum. And then what you do is you compare it to this this fancy plot of Planck, right? So Planck tells you here NS, right? This is the tilt we've been talking about. R is the tensor to scalar ratio. We've ignored the tensor perturbations throughout the lectures, right? These are the gravitational waves generated during inflation. If you put them back in the game, you get this two-dimensional plot. These ellipses are the preferred values, and the model we've been computing, the m squared phi squared, right, is this yellow up here. Spectral index is more or less okay, right? But the tensor to scalar ratio is way off. But that's just to show you, actually, I mean, one, how powerful these observations are. So we can really actually exclude models and test models. But also really also to make the connection, one forgets this, I think, a bit when one kind of gets sucked into these computations, but what we're actually saying here is that we have quantum fluctuations 13 billion years ago, and we're claiming that we can see the imprint of these and actually measure them and measure their properties in the CMB perturbations today. And I stop there.
Thanks, Valerie. Very nice lecture. One question by Marcus on the back.
Thank you, Valerie. Thank you for such a good lecture. So my question is about like the assumptions that we're making here, because I guess we're in a semi-classical approach in the sense of like space-time is a continuum, is classical, and we canonical quantized the perturbations of the scalar field. But I don't know if there is like any problem with that with initial conditions. Maybe in initial conditions also space-time should be quantized, or?
We do actually quantize space-time, because actually, so we said yesterday, right? We consider fluctuations both in a scalar field and in a metric, right? Fluctuations in a metric, and in particular, and then we saw we have 5 scalar degrees of freedom in metric plus the scalar field, and then we saw okay, actually only one of them is dynamical, and we're computing the scalar power spectrum for that one dynamical degree of freedom. Mm-hmm. But that's not necessarily the one just, I mean, that's really the only one dynamical degree of freedom that there is in this combined system. And that's also the one that we quantize, right? So, and here in the computation, in this gauge choice, I actually set delta phi, so the fluctuation in the scalar field, to 0. So this R that we've been looking at is really the psi, right? So the Newtonian potential. And that's the object we've quantized. So we are actually, I mean, this is, and I'm glad you bring that up, because this is actually a really important point, that actually the prediction that we have here assume a quantization of gravity. Right? We don't make any assumptions about how exactly a quantization works, just that it obeys the canonical commutation relations, right? But actually kind of observing these things, in particular observing the ones in the tensor fluctuations, right, which definitely have to come from the metric and could not come from the scalar field, would really be an observation of some sort of quantum nature of gravity.
Okay, thank you.
More questions?
I have 2 questions. The first, I didn't really understand where quantization actually enters into this derivation.
So we needed it here to get this constraint. If we did not have that constraint, then here, when we solve the harmonic oscillator, we would get the mode with minus a k tau, but also plus a k tau, right? So we would have different. We would have a second degree of freedom for the negative frequency modes, and the fact that we dropped that negative frequency modes is this condition here from the quantization.
Okay. How this affect the result? I don't really see it. Like.
Well, I mean, then you have to go. I don't think I can do it off the top of my head now. But then you have to add the second part here, right? And then when you solve the Mukhanov equations, right, you can see that here we only have the minus ak tau part, right? So then you would have a second part of the Mukhanov equation, second part of the solution, with the opposite frequency, and then you have to see how that traces through to here, right? Because that's where you have to plug the solution. So I can't tell you exactly what would change, right? And also the second part where it entered is that we say here that we really kind of have a harmonic oscillator, and we're in the ground state of the harmonic oscillator, right? I mean that's kind of another way to think of a quantum system, right?
Yeah, but here I can also see from GR that when I go to very small scales, the thing should reduce to a plane wave, just because you're basically in Minkowski locally.
Well, but then you don't know it's a plane wave, right? But I mean, any plane wave would solve the system, right? So you don't have to be in the ground state of the harmonic oscillator, right? You could be in any higher state.
Okay, yeah. Okay. Second question, maybe a little off topic, maybe not. How would you disprove inflation as a paradigm?
Okay, so one thing that inflation predicts is that there's super-horizon correlations in the CMB, right? And that's what we see. So if we had not seen super-horizon correlations in the CMB, then inflation wouldn't be there, right? Or if we would kind of see a universe which is homogeneous, which is not homogeneous and isotropic, right? Now, of course, you're asking me, okay, how, apart from the fact we already know, right, what could we do in the future? That is really difficult, right? Because also, you can, depending on the inflation models that you choose, your scalar potential, but basically depending on your scalar potential, right, your predictions for NS and R and whatever, right, can actually vary quite a bit, right? So not finding tensor modes, right, is compatible with inflation. Finding tensor modes is also compatible with inflation. There are some things. I mean, for example, the amplitude of the tensor modes is directly related to the scale of inflation, right? So if we either do or don't, as long as we don't measure tensor modes, we have an upper bound on basically the energy of inflation, right? Whereas if we do measure the tensor modes, then we would actually have a prediction for the scale of inflation. And then you could more indirectly think if this scale is compatible with all the other things that you understand from inflation. So for example, hypothetically, right, if you could build me a super good instrument which could measure the tensor to scalar ratio, I don't know, 20 orders of magnitude better than what we can do now, right? I mean, completely impossible, right? So that then you could prove to me that the scale of inflation is below BBN, then this would be dead. But unfortunately, that's completely science fiction.
Okay, I understand. Thanks.
More question for Valerie? In that case, I have one. Valerie, when I was taught that inflation would solve all the, was a success from the CMB perspective, I was taught that inflation would predict Gaussian distributed fluctuations as we measure them in the CMB. You didn't mention anything about this. Could you comment on that? Right.
Yeah, because we just talked about the power spectrum, right, and not the bispectrum, not the 3-point function. Actually, yeah, I wonder if that might also partially answer your question. So, but the thing is always, so the simplest models of inflation, right? So here we just looked at a 2-point function, right? But of course we have the solution, so now we can also compute 3-point functions, 4-point functions, whatever, right? And just in the same way, following to the same type of analysis, you can show that in this type of inflation models that we looked at, so really single field, slow roll inflation, we have a prediction that has to be very Gaussian, and that is indeed something that we can test with the CMB. Now, however, you can construct more complicated models of inflation, right, which do produce non-Gaussianities. So I think measuring non-Gaussianities would kind of maybe, kill the simplest realization, but would not kind of kill the paradigm of inflation.
But the fact that the CMB are Gaussian is another evidence.
Right. The fact that we see them Gaussian, the fact that we see them nearly scale invariant, right, which is exactly what we predict, and just the fact that we see them correlated on super horizon scales is also because what does it mean? Let me explain what it means, super horizon correlation, right? It means here we generated a fluctuation mode, right? We pushed it outside of the horizon. It then got frozen, right? Here, so this picture here. And then at some point it re-entered the horizon again, right? And it started oscillating again, right? And now the prediction of inflation is that this mode, when it enters the horizon, over the entire universe, this mode starts oscillating with the same phase everywhere in the universe, right? So you have a given perturbation mode, and it's described by a cosine, fine, but this cosine has the same phase everywhere in the universe in regions that are billions of light years apart and had absolutely no chance to talk to each other without inflation. So just these things just start entering and oscillating all at the same phase over the entire universe. Now, that, I mean, trying to explain that without inflation is difficult, right? You usually come up with constructing something which mimics inflation in some way.
Just to be sure I understand, so deviations from these coherents are called isocurvature perturbations, right?
Right, so isocurvature perturbation, so here we said we had one scalar degree of freedom, right? And that sets the perturbation, that and when it re-enters the horizon, right, sets the initial conditions for all the density perturbations in all the different components of the universe, right? And since we only had one scalar degree of freedom to start with, basically all other perturbations kind of follow from that, and hence they all obey the same ratio, right? And hence they are adiabatic perturbations. And isocurvature perturbations would now be if you had a second perturbation mode, right, which is independent of that, and with that different, I don't know, say your radiation component behaves differently than your matter component.
And that would be at both ends of the transition from superhorizon to subhorizon.
Yeah, so it's not so much that I wouldn't so much describe it as that the phase relation is lost. It's more that kind of the relative importance of the perturbations in the different components does not follow this prescription.
All right, okay, thanks a lot.
Valerie, different modes don't have the same phase, right? Now you have a given K mode, it had some oscillation,
right?
But you said that.
But in the power spectrum, that drops out, right? Because if you do the 2-point function, the phase drops out. So what I'm saying,
right.
So what I was saying here is that a given K mode across the universe, when it re-enters, has the same phase, right?
It had the unique phase, right? It froze oscillating.
Yeah.
I guess it continues to oscillate where it was left before.
Yeah.
Somehow, right?
Yeah.
Okay, but
right, different K modes have different phases.
Right.
Yeah.
So you cannot really observe the phase, can you?
But if I do, you can observe the phase in the sense that if you did not have this phase correlation, right, then when if you do the 2-point functions in different spatial regions, it wouldn't cancel, right? So you've you cannot observe the phase, but you can observe that it has the same phase and not a different phase, right? Otherwise, if you do the 2-point function of stuff which is incoherently oscillating, right, you will just average.
Let's discuss this over the coffee. You keep getting up.
Yeah. They're keeping you awake, right? So next question over there, right?
Yeah, thank you. I wonder how inflation theory correlates with our knowledge from QFT about renormalization of theories. Because as I seen on your plot, all like phi squared, phi cube, and phi to the fourth was already ruled out by Planck observations. So wonder if we just use quantum field theory for this potential, will it be self-consistent or?
Right. Okay. So when we go to this plot, so this is really so when we say here, for example, right, phi to the 4 is not even on this plot, right? Phi to 4 is up here, right? So this really just refers to just completely constant. So when we did m squared phi squared, right, we just took completely constant mass parameter, right? If I do phi to the 4 in this framework, right, I would just take lambda to be constant, right? Then I do the computation. Now, of course, you can do more involved stuff, right? And you can take into account the running of the coupling. Now, it's not okay. So typically, that's still not enough, right? Because like if we do phi to the 4, right, even if we take into account the running of the coupling, it's still the potential tends to be too steep. which means you get a too large tensor to scalar ratio. However, you can still do relatively simple model. I mean, then you can either you can do different things. You can either kind of write down a slightly more involved scalar potential, but you really don't have to do extreme stuff, right? You can write down slightly more involved scalar potential, or you can play a bit with coupling to gravity. So, for example, these models which fit very nicely, they tend to have a coupling between the Ritchie scalar and the scalar field. And then you can you flatten out your potential effectively, and you get nicely into this region here. So it is kind of consistent with really a proper QFT treatment. This was just kind of an oversimplified treatment.
Okay, thank you.
Okay, Vitor, finally, I think you can. Let's thank before Valerie again for her great lectures.
Can you hear me well? Perfect. So it's great to be here again. Today I would like to basically use the first two lectures to tell you how exactly we can use this for detections and for the next few years. Now, the upshot of what we saw until yesterday was the following. First, I know how matter moves in black hole spacetimes. There's two features which are interesting, meaning null particles get stuck, get trapped in something that we call the photon sphere. It's an unstable trapping, so it leaks out eventually. And when you're trying to do wave dynamics, so you fluctuate the black hole spacetime, you're able to show that massless fields, all of them seem to obey. Well, they don't seem to obey. They do obey a second-order partial differential equation that looks like this. It's a wave-like equation. R star ranges from across the full line, minus infinity at the horizon, to plus infinity at spatial infinity. And the potential is just something that tells you about the space-time structure. Now, it's interesting that if you plot this potential as a function of R, or R star, can you see this, by the way? Roughly. Well, maybe I should put it here. I just need them to see the rough, not details of this, okay? So if you look at the potential, it looks like this. There's structure in some space-time region, and then it's zero at the boundaries, okay? Now, this location is to a very good approximation the location of the photon sphere. So if the black hole is non-spinning, this is roughly 3m, okay? In fact, it's exactly 3m when the index, the angular momentum index, phi L, remember we expanded this in spherical harmonics, so it's exactly 3m when L becomes very large, okay? So all the non-trivial structure of space-time seems to be encoded really in the light ring, okay? So something is going to happen because of that. If you send in a scalar wave or a gravitational wave, it sees stuff at the light ring, so we gotta understand what. Now, we also saw that if we look for static solutions of this equation, there aren't any, okay? So we need to understand how exactly we get to the no-hair result. What happens if we throw something on the black hole spacetime? Let me also finish with two things, this brief recap. The first is that because far away the potential is trivial, goes to zero, and because we're setting C equals G equals 1, this means, of course, that all of these massless fields, including gravitational waves, travel with velocity 1, so at the speed of light in Einstein's theory, okay? The second thing I want to say, and that will be my final lecture, is this is true if your space-time is not spinning, okay? Meaning you can recover this really nice wave-like equation because there's no spin. But if you think about, for example, the Klein-Gordon equation on a Kerr geometry, not in Schwarzschild, but in Kerr geometry, you see that you have cross terms time azimuthal number there, right? So you expect to see cross terms here that go like dt d phi, okay? And that will have an impact in conservation quantities for us, okay? Very good. So we started trying to understand how we solve this, and the basic stuff is just do some scattering experiment. I'm not going to even open the notebook. We understood there's some notion of energy conservation. We know roughly how to study this problem. But now let me try to actually do physics, okay? So let me try to solve this equation generically. Now, so the source term is zero, meaning I don't have any scalar charge here or a mass or a charge sourcing the Maxwell equations or the field equations. You could do that. If you repeat all we did, you're going to find that there should be an extra source term here that depends on where exactly. So if, for example, if I'm waving my hand close to a black hole spacetime, you can do the calculation, just use the notebook. You're going to have some source term here. If my hand is sufficiently small or much smaller than the black hole, this is really just going to be some delta function of where exactly my hand is, okay? But even without this source term, there's non-trivial solutions to this equation that come from initial conditions, okay? Now there's different ways you can use to study this. I'm just going to Laplace transform that equation, okay? And Laplace transform means, well, I just assume this decomposition for my psi, I insert this in the wave-like equation, and you're going to find that time derivatives go away, and the only thing you get is an equivalent source term, this guy over here, that tells you how exactly psi and its derivative looked like at t equals 0 initially, okay? Again, psi can be anything, a scalar field, Maxwell field, or a gravitational wave. Okay, so we need to just solve a very simple ordinary differential equation. To solve this, we need to impose boundary conditions. The boundary condition is everything that gets close to the horizon should just enter the horizon. So ingoing waves at the horizon. And at infinity, I need to know exactly what's going to happen. Now, there's different things that physically could happen. There could be somebody far, far away from the black hole waving his hand, generating waves that travel inwards. I'm only going to focus on systems which are totally isolated, okay? So eventually I want to look at a black hole spacetime that's only emitting stuff outwards sufficiently far away from the black hole. Which means eventually I want to require that this guy, I want to require only an outgoing piece for this guy, okay? Now the solution, the general solution to this problem, you either use the Green's function approach or something called variation of constants, goes as follows. You define two homogeneous solutions, so you set this guy to 0, you solve the system. There must be two independent solutions because it's a second order system. I'm going to call these independent solutions the left moving guy, meaning it's a solution that behaves well at the horizon. And the second independent solution, I'll call it the right moving guy far away. It's a solution that describes outgoing waves far away. Okay? Once you have psi L and psi R, then the full solution to this problem, the non-homogeneous problem, looks like this. Okay? It's a combination of the two homogeneous solutions. And that's it. You're basically done. Finding them, it's in the scattering notebook. You just start somewhere. For example, if you want to use psi, if you want to calculate psi L, you just start the integration of this ordinary differential equation sufficiently close to the horizon with this boundary condition. And then you let some Runge-Kutta integrator do the job. Okay? Same thing for the right moving guys. Okay. Now, so you see, we are working in the frequency domain. So if you want to have the full solution, you want to solve this for each frequency. Okay? And of course, then if you want to actually do a time evolution, look at the time dependence of your solution, you need to do the inverse Laplace transform. That's done in the notebook. Let me take a few seconds to look at it because this is interesting. What the heck? Okay. Very good. So there you go. The only thing I'm doing is integrating the equation, which I rewrote in terms of R and not R star, okay? So this is not a black box, it's really soft numerics. It just uses a Runge-Kutta integration method for this guy. And then, of course, you need to do a numerical integral for each frequency, okay? Now, this was done in the 70s. There's a nice, beautiful Nature paper doing exactly what we're doing here. So this is what happens when you throw in a Gaussian packet, meaning the solution at t equals 0 for your psi is some Gaussian distribution centered somewhere, right? You take a Gaussian wave packet, you let it go, and you see what happens. This is an experiment by Vishveshvara in 71. When he calculated, I did that in the notebook, okay? When you do the time evolution of this field, this is what you find. So I'm sitting at 100 m, very far away from the black hole, okay? I let the Gaussian wave packet of field go, meaning psi at t equals 0 looks like this, e to the minus r star minus r0 squared. Okay, it's centered somewhere. The details are not really relevant, okay? And then you wait. Okay, here time flows to the right, and this is what you see. You're sitting somewhere, the Gaussian wave packet goes, you see no signal at all initially, okay? And then at some point, a fraction of that Gaussian hits you. You start measuring some field. Again, this field could be a gravitational wave, okay? And you wait, and you realize, oh, nice, the field goes up, there's a peak here, it oscillates, and then it dies off. I mean, you'd kind of expect that. There's no other way for this to go, right? But then you think, oh, okay, let me change the parameters of my Gaussian. Let me change the width and the location of my Gaussian. What happens? So when Vishveshvara was doing this, he was repeating all of this, calculating all of this, and he realized that the way that the field was dying off was always the same. Meaning, this decay timescale over here and the ringing frequency was universal. It didn't really depend on what exactly you were throwing at the black hole. It was always dying off in the same way, okay? Which means you're actually looking at something that's characteristic of the black hole, okay? This is the outcome of the numerics, so we can try to understand this a bit better. By actually trying to do ourselves the integral. So remember, the way this goes is you calculate the response in the frequency domain, and then you need to invert back. And there's two ways. Numerically, you always do it on the real line, but you can use contour techniques, right? You can close the contour of integration in the complex plane. Okay? Now, when you try to do that, you're going to find that there's special locations in this complex frequency plane that correspond to poles of your Green's function. And if you look at the response, let me go back here. If you look at the response, the general solution looks like this. You get homogeneous solutions, okay? One that goes to the right, the other to the left. And then you need to integrate the source term, this I, with one homogeneous solution, and then divide by the Wronskian of these guys, okay? This is the key piece. The Wronskian is evaluated here. It's really just 2I omega times A in. Let me show you what A in is. Okay? A in is the ingoing piece of the solution that behaves well at the horizon. So let me try to summarize what's going on. You start with a wave that's ingoing at the horizon. So let me put here the correct solution. This is my psi L. Okay? Generically, a wave that does this will have an outgoing piece far away, A out, okay, and some ingoing piece, A in, okay? What we find is that for certain frequencies in the complex plane, this term is 0. A in is 0, okay? So we call this the quasi-normal frequencies of your system, and they're basically they're the stuff you would calculate if you were trying to look at the spectrum of a black hole, right? If you think about the spectrum of a string, the only thing you do is you take the wave equation, you impose boundary conditions where you want them to, and you solve the problem. There's only a set of frequencies that actually solve that, right? Black holes are exactly the same, except that it's a dissipative system. So these guys will lie, in general, in the complex plane. Very good. Now, there's also an interesting feature. If you're doing LIGO physics, LIGO is really located far away from the black hole. So you can take this expression far away. And when you do the limit that you're looking at far away from the black hole, so R star goes to infinity, this piece over here cancels, and your response, the thing that LIGO is measuring, actually looks just like this, okay? That's the only thing you need to calculate, okay? So when you're doing the inverse integration to get the time response, well, you're going to get poles here. These poles are these crosses here, okay? There's also a branch cut at 0 frequency. I'm going to not even mention this guy. But the response, because there's poles in the frequency plane, you can immediately guess that the signal is going to look like some exponentially damped sinusoid at those locations. Okay? And of course, this corresponds to having A in equals 0. I added a notebook. Actually, it mimics what Chandrasekhar did in 1975, okay, to calculate these numbers. The only thing you do is you integrate from the left, requiring this boundary condition. You integrate from the right, requiring the correct outgoing boundary condition, and you try to match these solutions at some point. You will find that a numerically stable solution happens if you do the matching close to the light ring, although it's not, totally necessary that you do that, but you find it's really stable if you do that. So the solutions are in this plot over here. This gives you numbers, complex numbers, and there's an infinity of them. Now, this potential V depends on the angular number. If you remember, it was like L plus 1 over R squared plus something. Okay? So these numbers will depend on L, and at fixed angular number, you get an infinity of characteristic frequencies. Really, this is not different from doing the spectrum of the hydrogen atom. It's exactly the same. You got S waves, P waves, and so on. These are the energies. Now, they lie on the complex plane, meaning they will have a real component and they will have an imaginary component. The imaginary component, if you let me erase this guy. The time dependence of my field, of my gravitational wave, for example, was written in this way. E to the minus I omega t, okay? So the time dependence now will be dictated by this guy. Fortunately for us, the imaginary component is always negative, which means fluctuations decay. Omega I, and because they decay, it means black holes are stable. You kick them, and whatever you use to kick them eventually is going to die off. Okay? At least for non-spinning black holes. And of course, if LIGO is ever going to see this, and it has, the most important number here is the number with the smallest omega I, right? That's the guy that lives the longest. Okay? So the relevant timescales are always 1 over omega I. So if you look at this plot, you can, I think you can, with the notebook, you can calculate like 10 of these numbers. Basically, you're looking at this number over here, okay? The guy closest to the real line. Very good. We've been doing this. There's an industry for this. We've been doing this for decades. We know everything about how black holes vibrate. And here you go. If you look at very large angular numbers, L, okay, this would be the high up hydrogen atom states, if you wish, then we know the asymptote to this number. Log 3 over 8 pi, Bekenstein was really thrilled with this asymptotic behavior. He thought it was related to black hole quantization properties. And then integer, okay? This gives you the infinite family of solutions to this guy. Now, these modes really are not relevant for LIGO because the imaginary part is so large, they die off immediately, okay? What's relevant for LIGO is the fundamental mode, the dominant mode, which for L equals 2, let me write this here, for L equals 2, gravitational fluctuations, then m omega is of the order 0.37 minus 0.089 I. And if you remember how we rewrote mass in terms of seconds, okay, then we are looking at frequencies that lie where? Where exactly? What does this correspond in terms of period of the wave? Anybody remembers? A solar mass was 10 to the minus 6 seconds, so that's what we're talking about. For a solar mass black hole, we're talking about a microsecond period. If you make the black hole larger, then, well, the period just increases. So periods of oscillation scale with the black hole mass. Okay? So if you take something that looks at supermassive black holes with 1 million solar masses, then this guy will see periods which are, of course, 10 to the 6 times larger. Right? The idea is always that you're looking for stuff that moves at the speed of light. So you need these waves to have time to cross the horizon, roughly, or the light ring, and see the entire global structure. Very good. This also tells you exactly what you expect a gravitational wave detector to see. Okay? So you throw, let me admit I throw this marker onto a black hole. Okay? You just do this. The guy is being accelerated, so you're going to have some Bremsstrahlung gravitational radiation. So there you go. You throw your marker down the black hole. There's some prompt radiation, stuff that seems to travel on the light cone. So if you're sitting here, if LIGO, your detector, sits here, it's going to start seeing something that came directly from the object. Okay? As the guy starts falling, two other things happen. First, some of the radiation doesn't need to go directly to you. It can be lensed. It can live a long time orbiting the photon sphere. Or if you remember, again, in the wave language, stuff that's hovering around the peak of the potential. Okay? So you have another component of the signal, which I'm going to call ring down, just this black hole vibration. Okay? But at very late times, some of the signal that was supposed to go elsewhere really just gets backscattered by curvature. Okay? So the response that LIGO or any other gravitational wave detector see in curved spacetime is far from trivial. It's not the on-light cone thing that we get used to in electrodynamics, for example. By the way, this is also, I'm not going to discuss this, but this also poses an interesting challenge, right? So, suppose I ask you, how do we know, how can we find proof that there's an horizon in the spacetime? You know, suppose I'm after showing that black holes exist. How do we do this, right? Suppose I very carefully construct an object that looks like a black hole, right? But let's say I surround this guy with a mirror very close, but on the exterior of my black hole. How exactly would I know that there's structure there? How do we do this? Because the response that my detector sees doesn't, you know, it's not totally related to the horizon. It depends on prompt emission and then the vibration mode of my spacetime. But the vibration mode, this ring down, only cares about the photon sphere, right? This light ring. It doesn't care about the horizon, right? So even if you change, carefully at least, stuff near the horizon, you're going to have a hard time telling it apart from a black hole. Very good. So this is a typical waveform that LIGO would see, and you can calculate this in the approximation we're using, which is something disturbing a black hole spacetime. just with this formalism. Okay, you take a black hole spacetime. Now you place a small star around the black hole. The small star is a fluctuation. It's described by this equation with a source term. We know how to solve this equation, so we know everything about the problem. Okay, that's what we've been doing for decades now. Of course, to prescribe the motion, we've been using geodesic equations, right? And the geodesic equation assumes some conservations, the energy and angular momentum. But once you place this guy there, well, the solution itself, psi, is carrying energy away to infinity. So of course, there's going to be some back reaction on the motion. But you can estimate it precisely by calculating fluxes far away and then back reacting on those quantities which are no longer conserved, energy and angular momentum. So you do some kind of adiabatic evolution of your parameters, and you can do it. Okay? You will always find something that looks like this. Your field psi, okay? So if you do a small star around a black hole, your field psi will always look like this. Okay? So you have a small star on circular motion. The gravitational wave amplitude depends, of course, on how far this source is. You're emitting gravitational waves, so of course you're losing energy. The only way to conserve energy is to move inwards, right? But when you move inwards, well, then the frequency, if you think about Kepler's law, the frequency has to increase. The velocity increases. This source is going to increase, and this tunes the amplitude of your wave to be higher. This is why you see a frequency increasing and an amplitude increasing. We know exactly how to do it. It's a very simple 5-minute calculation that you can do just to understand all of this. Okay? We call this the chirp signal. These guys are just getting closer together. Frequency and amplitude are increasing. Looks like the song of a bird. Okay? But of course, there must be a point where the star is so close to the black hole that it collides with the guy. Okay? There you go. Roughly, this happens here. The star collides with the black hole. We knew already that we can't destroy, we saw this yesterday, we can't destroy black holes. So the final state of this collision has to be a black hole. There's no hair, there's uniqueness properties. We have to have a black hole at the end state. Okay? But now we see how exactly you get to that end state. Right? You fluctuate, you throw something at a black hole, the guy takes the fluctuation, okay, you just have gravitational wave emission, and then at late times, the no-hair property of black holes is reached via quasi-normal ringing, via the black hole just ringing down as a church bell or whatever, as a guitar string. You just damp out. Okay? Very good. For a 10 solar mass black hole, these are the numbers. So if you take a 1 solar mass black hole, or a 10 solar mass black hole actually, this is roughly what LIGO has been seeing for the last few years, then the frequency of oscillation of the final signal, of the final piece of the signal, is roughly 1 kilohertz, and the lifetime is roughly 0.5 milliseconds. Okay? Good. So this is the fundament. This is the guy that lives the longest. This is the mode with the smallest imaginary part. There's other modes, and there's been a huge discussion, which is ongoing, by the way, in the last 2 years over whether or not we can actually see other modes. But I'm going there in a few seconds. It's still impressive, no? I mean, this. So if you think about a 10 solar mass black hole, by the way, what's the size of this black hole? Anybody knows? What's the size of a 10 solar mass black hole? Okay, roughly 30 kilometers. So just think about this. It's a city. No, it's a huge guy. It's a huge guy that rings on a scale of a kilohertz. This is super quick, and it dumps on a scale of a millisecond. So you have a city, you fluctuate the city, and this fluctuation dies off in milliseconds. It's totally impressive. Okay? Of course, the reason is that the system is responding at the speed of light. That's why the scales are so impressive. So you can use this stage to actually do physics. That's what LIGO is doing. That's what we will be doing for the next decades. Okay? How do we do this? Well, we understand this because the star was just eaten by the black hole. The final state, so if you look at very late times, you're here, you're going to see just a black hole, right? So if you move backwards in time, so if you're in this direction, you're going to start seeing a slightly disturbed black hole. Slightly disturbed because the guy just ate the star, right? So it should be ringing down, vibrating in those frequencies. But the final state, the black hole here, we saw that we only need two parameters to characterize the black hole. The mass, m, and the angular momentum, a. Any black hole in the universe is characterized by this, okay? Well, if you believe the uniqueness result. Mass and spin, and you're done. And this is great. This is great because if you measure one of the modes, meaning you measure the real part that tells you this oscillation frequency, and you measure a damping time, then you have two quantities, right? But these guys are calculated on the black hole background. So omega r and omega I mean, they have no choice. Once you give the code that you have, the mass and spin, they are totally determined. So mass and spin characterize completely omega r and omega I. So if you measure observationally one of those frequencies, you're done. You have a way to estimate mass and spin of black hole. Okay? And of course, if you're lucky enough that you can actually measure more than one, this is going to be actually a superposition. There's actually a superposition of modes here. So if you measure more than one, meaning you measure more than one omega r and more than one omega I, if you think about the hydrogen atom, it means you're distinguishing different levels. Then you test the theory. So one of these modes, you measure mass and spin. Then you go to the second, you're testing general relativity, right? If it doesn't agree with the first measurement, something is wrong with the theory, okay? And if it does, well, brilliant, we have another test, okay? So this is what LIGO did in the first event, GW 150914. And this is how they showed it. It doesn't look impressive, but it is impressive. It's the first spectroscopic measurement, if you want, of black holes. Here's what they did. They have a detection. It's a beautiful detection that stands out in the noise. Okay? They used the increase in frequency and amplitude of the signal to actually estimate the mass of the black holes there, of your objects. Okay? That estimate is this solid black line over here, the 90% posteriors. Let me remove this. Okay. Okay, so the black solid line is what we expect from measuring the Keplerian phase, how this frequency and amplitude is increasing. Okay. Now, they are going to do spectroscopy, meaning they take this signal, it's not as beautiful as this one, but almost, and they start feeding the late stage, so after the guys collided, you have a single vibrating black hole. They start feeding this to an exponentially damped sinusoid. So they measure omega r and omega I. Okay? Now, if you try to do that, this is a useful exercise, you'll understand the problems of doing this. Okay? And the first problem, and it's still the outstanding problem in the field, is what is the problem? What happens? I mean, if you try to do this, what's the first thing that you need to solve or to understand? Hmm? Yeah, you have the signal. I give you the signal. LIGO, this is public. I give you LIGO signal, and I ask you, oh, please calculate omega r and omega I. Or I give you a pure signal. This pure signal, there's no noise here. What's the problem that you're going to face immediately to calculate omega r and omega I? Yeah, but even, yes. What we did here was assuming that the second guy was very small. But even if they are two equal mass guys, this stage, we know it. Because, at late times, it's really just a vibrating black hole. But still, there's a very simple problem, immediate problem that you're going to face. Maybe you guys don't have it. I should talk to you. Well, the problem is, you're trying to fit a time domain signal, this guy, okay, with an exponentially damped sinusoid. So you have your signal. Let me erase this. Psi of t, okay? And you want to say that your signal is e to the minus omega I t, so it's damping, times the sine of some ringing guy. Maybe a sum of these guys, but let me just start with one that's simpler, okay? Clearly, I mean, we did all the calculations here. I mean, I didn't omit anything, okay? But we know this is only a good description when your space-time is a slightly disturbed black hole. It's here. Clearly, this is not a good description here, right? Because the black hole is not isolated, it's not ringing down. You're exciting the guy, right? So the question is, when do we start the fitting? What's the origin of time here, right? So when do we start the procedure? No, it would still happen. You might know it would still happen. That's a great question. It would still happen because even if the second body is negligible, you're stirring the black hole up. Let's assume that I have a small star. I'm stirring the black hole up. Amplitude is going up, frequency going up, and then the guy dies off. And you think, okay, it's this moment that's triggering this. But it's not true. Because before the collision, you see waves were already being sent to the photon sphere. They're circling there just waiting for things to happen. Wait. So the start of this ring down is far from trivial. We don't understand this. I mean, you can try to phenomenologically capture this, but we don't know at the theoretical level what's going on. And I don't think we should know, okay? But so what LIGO does is get a workaround. So they start the fitting time at different times. So they do this. They find the peak of so you have a waveform that looks like this, and then it dies off. This is the peak of your waveform. So they do the following. First, let me assume I fit to an exponentially damped sinusoid 1 millisecond. Let me see if I don't screw up. 1 millisecond after the peak. Okay, so they identify the peak. They go 1 millisecond after, and they fit. Okay? And they get this 90% posterior. So this is relaxation time, vibration frequency. Okay? Now, you'd expect that it's not a good idea to do this very close to the peak. Why? Yeah, because the hole is not yet totally free and vibrating, right? It was a nonlinear stuff that was going on. So you might think, well, I want to do this very late. So that's what LIGO did. Then they do it for 3 milliseconds after and 5 milliseconds after. And what you see is, if you do it too early, there's no agreement between the ring down expectations and what you'd get from the in-spiral guy, right? But at late times there is. Of course, there is a price to pay in this game. And the price to pay is, if you go too late here, your signal is so weak, there's so little left of it. You're really just bumping into noise. And this is why the 90% curves look awful, right? These posterior distributions look so big. Now, if you're looking at this plot, I'm sure you're not impressed, but you should be. This is the first time that we use the black hole spacetime and that we're doing spectroscopy on it, okay? We're measuring stuff that's orbiting the black hole at the speed of light that's trapped in the photon sphere of the black hole. Okay, we're looking at waves that were there for a while. Hey, it's amazing, huh?
So besides the agreement with the expectations, is there any a priori, calculation which will tell you which is the optimal time to obtain this?
Right.
Correctly?
So
I mean,
good.
what you were asking us before.
So this is the work of the last year. I think there's like 5 or 10 groups that have been doing precisely this. They took a suite of non-linear calculations and they tried to find what's the ideal time to do this fit that agrees with everything we know. The conclusion is rough. If you don't want to be super precise and you start the fit 10 m after the peak, you're fine. Okay, so if you start 10 m after the peak, you're fine. There was a claim 1.5 years ago that actually we could see 2 modes in the signal. Not only we see the fundamental guy that lives longer, there was evidence that we also saw a second mode that was died off faster, okay? And that would give us a test of general relativity. Unfortunately, in the last half a year, there seems to be evidence that really this is just noise. So I don't think we're
what
there
about
yet.
ratios of the frequencies?
Oh, sorry?
Ratios of the frequencies of different
So,
normal modes?
good. So the frequency itself is roughly the same. So actually you can check it here. These are the numbers, by the way. I mean, I'm not doing anything. So the frequencies, you measure them on the real axis, okay? So they start, the mode you want is, so L equals to the dominant guy. The dominant mode is the mode that acts on a larger scale. For gravitational waves, this is always, or almost always, the quadruple mode, L equals 2, okay? L equals 0 and 1 we saw had no information because it's really just redefining mass and spin, okay? But so the frequency, so the frequency doesn't change a lot. If you look at the numbers closer to the axis, these guys, the frequency is really not varying a lot. What's varying substantially by a factor 2 or more is the omega I. So the damping time really becomes a very short quantity. Okay. Now this was done. So LIGO has been doing this for this kind of stuff. The first event is still the loudest event, but the signal to noise ratio, that gives you a measure of how important, how clearly I see the signal, is only about 7 in the ring down stage. So it's not a lot, okay? But you can think about what's going to happen in the next few decades. This is one example that one of my postdocs did for the next few decades. You see, assume that you see a merger, you see a collision between 2 black holes, and you see it with a signal to noise ratio of 40, okay? So a few times large, not much. We will do this in a few years. You will do this in a few years, okay? This is the stuff you do. So with this signal to noise ratio, okay, you can repeat that game and you're going to find, you're going to find that mode that LIGO saw, that band that was huge, now is going to look like this, okay? Time, the damping time scale, and the frequency, okay? Roughly for the same black holes, for the same masses. But now, at signal-to-noise ratio of 40, we are going to be able to see the next guy, the octopole mode, L equals 3. Okay? And you see, there's no overlap. This is a beautiful test of general relativity that we will be doing, I don't know, 10, 20 years. Maybe I'm being a bit optimistic. Now, there will be a space-based European detector, LISA. This is signal-to-noise ratios of 40. LISA is going to see stuff with signal-to-noise ratios of hundreds or even thousands. Okay, so black hole spectroscopy will be a big thing, will be a huge tool to test GR. Before, do I still have 2 minutes? Okay. One of the things that we thought we understood for decades, Kip Thorne has a review on this stuff, is, well, how is gravitational wave emission changing if we take into account the environment? You know, we're doing curved black holes, come on. I mean, curved black holes are vacuum. These guys live in galaxies. You take a 30 solar mass black hole, it's inside a galaxy of 10 to the 11 solar masses. How are you really sure that you want to spend €1 billion to build a guy based on this assumption? You know? Now, there's a review a few years ago, well, actually many years ago, that claims that surprisingly the effect is negligible. So you take all the environment you want, and as long as the densities are small enough, you're still fine. You're still fine to scales of 10 to the minus 5% or so. You can do tests of GR, you can do black hole spectroscopy. Don't worry about galaxies, okay? Now, a year ago, however, people saw the following. I'm trying to summarize, okay? This is not the entire story, but this is what they saw. They were trying to mimic the environment, okay, by changing a little bit this equation. Remember that the potential summarizes the structure, right? It comes from the metric. So the idea is, well, okay, let me see this guy sit in a galaxy. I'm going to put some accretion disk, some dust over there. There will be a rocket somewhere close to the black hole. That's going to change this V, okay? So they did the following. They took the original vacuum potential, and they said, okay, I'm going to just add a small bump far away, I don't know, some star or some flying comet, okay? That's going to slightly change the potential. It's going to slightly change it by an amount proportional to a quantity epsilon. This epsilon is very small, okay? And the bump is located a distance A away from the black hole. Okay? Now, your expectation is you repeat all of this stuff, you get the same. Right? So it was a huge surprise when they used the notebook that I sent you to calculate the new frequencies, omega r and omega I. The numbers are here. Okay? This is omega I and omega r for different bump location and for an epsilon, which here is, I think, 10 to the minus 6. It's really a small guy. So you have this V is of order 1, 0.6, okay? And this guy, epsilon, is 10 to the minus 6. There should be no difference. Okay, the numbers should be the same up to 1 part in 10 to the 6. Okay? And this is what you see. You see omega I starts here and omega r, these really the black hole numbers. And they can change by factors 2, 3, 10. You can change the relaxation frequencies by orders of magnitude if you place the bump sufficiently far away. Everything seems to be unstable. How can we trust anything that we've been, how can we trust what LIGO has been telling us? Okay? Actually, fortunately, we knew this problem in quantum mechanics. There's a name for it. It's called the elephant and the flea. Okay? The elephant meaning being this guy, the original vacuum potential, and the flea being this small bump. And the problem in quantum mechanics was if you do the calculation of the spectrum of this system, the flea seems to be disturbing the elephant a lot. Okay? But you can't, I mean, if we trust physics, this shouldn't be happening. So we now understand what's going on. And it tells us the limits of doing things in the frequency domain, which is also why I started it this way, okay? If you actually look at a time evolution of your system, okay, instead of looking at spectrum and characteristic frequencies and so on, no, you repeat what we did. You take a Gaussian wave packet, you throw it on this black hole with some bump, and you see what's going on, okay? And this is what you see. So this is for an example with a bump, a distance of 30 away from the black hole, and an epsilon 0, so this is vacuum, okay? And then epsilon 0.1. You can do it for 10 to the minus 6, 10 to the minus 10, and so on. And you always find the same thing. What you find is the following. In the time domain, when you actually look at the signal, the initial stage, so this part over here, is the same for all of these guys. Okay, the black hole really is relaxing because of the light ring. Gravitational waves are trapped in the light ring. It doesn't care about the bump, doesn't care about anything else. It's the near horizon stuff, okay? But then, when you place the bump, what's going to happen? Well, there's these ring down waves, they reach the detector, but they also see the bump. And a fraction of them, a very small fraction of low frequency, sees the bump, is unable to cross the bump, is unable to tunnel out, if you wish, and gets stuck there between the peak at the light ring and this bump. Okay? So the end state of this, when you look at the signal for long times, okay, seems to be that the decay of your field is not the vacuum case, it's slower. So everything is consistent, right? The frequencies really change a lot, but they don't tell you what's going on in the time domain, right? So the flea is there, but it really makes a small bite at early times. At time scales that are short enough for LIGO, these time scales, we get exactly the same physics. If you have a good detector, and if you're willing to wait enough time, then you're going to see imprints of this map. Yeah, we have seen this, because you see, the amplitude of the signal is going down exponentially, right? And LIGO is unable to see further.
Okay.
Okay, I'll finish here. Thank you.
Thank you. Questions, comments?
Hi, thanks for the beautiful talk. I have a question about this very last plot, just to make a connection with the previous thing we were talking of, where should we start measuring after the peak. Now, how do the numbers in the x-axis of that plot correspond? So that time scale that we are thinking about, should I be 1 millisecond, 2 milliseconds after the peak? Where is that in this plot? Like,
oh, you mean here?
Yeah.
So it depends, of course, on the mass of the black hole, but for a stellar mass black hole, we're always talking about millisecond. But this is more than that. So this discussion tells you that if you want to fit properly this ring down stage, you should start, let's say, 1 millisecond after the peak here. But now in this context of the flea, you have to stop before the signal reaches the bump. If you want to do a proper job at understanding the light ring, you should stop the fit at these stages. If you use the entire time signal, you're going to get crazy results.
Right, so you're both constrained from both sides, let's say.
Yeah.
And the region in the middle, is it like long in which time scale are we talking
You
about?
mean this one here?
No, like the region in between when this thing is
between
valid
here and here.
and when this starts failing.
Yeah, so roughly this is given by a light crossing time between the light ring and where you're placing the other stuff. So you can fit properly and find good results that relate to vacuum on these timescales. If you do it on larger timescales, things are not good. We don't know. Actually, we don't even know how the other modes behave in this picture. I mean, this is very recent. We just started to understand this.
Okay, thanks very much.
Why While I go to the next one, what if instead of a flea you have a dog or a rhino or something like that? I mean,
That's a good question. Actually, this started because of the dog. The first work, they didn't do a bump. What they did was a high frequency fluctuation on top of the potential. And they saw something amazing, which is the fundamental mode was stable. It wasn't going anywhere. It was always there. But the higher modes, the modes that we thought we don't care about, were all being destabilized. And this came out as an attempt of saying, no, I'm also able to destabilize the fundamental mode. So being a dog or makes a difference.
Yeah, thank you. I have a question. Are accretion disks important? Because I guess I'm not sure about the orders of mass, but
they
they're
are.
very close.
So they are depending on how good you are. Meaning, for the next, 30 years, we are not going to be able to see signals past this point. Okay? So for those detectors, for stuff that we'll be doing in the next 3 decades, the accretion disk is irrelevant. The accretion disk is going to do exactly this sort of thing. Okay? At late times, if you're extremely good, if you're able to clean your signal of everything else that's coming, then eventually you are going to see this. And then the accretion disk will have an impact on wave emission. Right now, I think we can rest assured.
Okay, thank you.
thank you. More questions, comments?
I have a question regarding the analysis that they do for the quasi-normal modes. Do you know why they are fitting it in time domain and they do not look at peaks in the frequency domain?
They actually do.
They do.
Yeah. There's different groups. I think most of them started in the frequency domain, but now there are groups doing it in the time domain as well. Yeah.
Okay. But there is a difference why like one analysis is better than the other respect the signal.
I don't think I would call it better. It's just that if you do it in the frequency domain, you are filtering some components of the signal, either low or high frequency. That helps sometimes, but all of this is done at a phenomenological level, to be honest.
Okay.
Because we don't understand the theory, we don't understand the so you see, even a basic thing like the excitation of these modes. I told you that omega r and omega I are universal numbers. You give me the black hole, I give you the numbers, right? You give me a guitar, I tell you the frequencies. But we don't know the amplitude. We don't know who's playing, how loud these guys are excited. We don't know it from first principles. We can run nonlinear simulations and roughly estimate this, but we don't have a good control even of the amplitude. So there's a lot of things we need to understand and refine.
Okay, thank you.
More questions, comments?
I think there's a question.
Yeah, a question about like the nonlinear solutions. Would that give you more information about the black hole? Like will push towards like the full data set that you have?
Oh yes, yeah.
Actually give you more information and
Yes.
restrict your
Yeah,
parameter
yeah.
space.
I mean, we can twist this whatever way we want. But if you give me this, so I've been arguing, because that's what I like, that black hole spectroscopy is great. I take the relaxation of the black hole, I look here, and I say, wow, gaze and admire. I mean, I can do the calculation of the mass spin of the black hole. I can test GR just using this. But nothing beats the entire information, right? If you give me all of this, for sure I need to be able to do a lot more. Now, period. Okay. This is the best we can do, is take the full signal and make sure that what we see is compatible with GR. And it's fine, it's going to work, it's working. The slight problem is, if you actually want to test the theory, you need to go outside the theory, right? And we have no idea how to do nonlinear evolutions of generic theories. But we have a very good control on how to do black hole perturbation. It always works this way. Right? You just want to know your background state, you linearize that, and then you calculate this. This we know how to do. It's a solid, robust, general calculation. Doing non-linear evolutions, I mean, each of these guys takes a couple of months to run.
Okay.
Right?
So is it a problem of the time nonlinear, like it will take to compute the nonlinear equations, or is it about like the nonlinear equations themselves?
Yeah, it's both of them. So it starts off by, you know, each simulation takes, as I said, depending on how long you run it, a couple of months. But we can do it, and computers are getting better, so that's not really the issue. The issue is, if you give me a generic theory, it's gonna most likely not be a well-posed theory, meaning it doesn't admit a well-posed initial value problem. Why? Because most of the theories you can think of have higher than second time derivatives. And if you try to mathematically look at where is the solution going, you can't do physics. You can't predict the future. That's a real issue.
Yeah. Yeah. But in principle, under general relativity, like standard one, you will be able to do this.
Yeah, that is fine. Yeah,
okay.
yeah.
Okay, thank you.
But by the way, even having environments, so you take, instead of vacuum, you just start adding stuff. Even this is so challenging, we're just starting.
Right. Looking at the cartoon, do we expect that it's really the tidal forces deform the black holes from this spherical?
Excellent question. So tidal forces do deform black holes geometrically. I mean, we know how they change the area. But we just saw yesterday that even though the horizon is deformed, they don't polarize. So the gravitational field of this deformed black hole is identical to the one of the black hole in isolation. I don't think I or anybody has a satisfactory explanation for this, or some analogy for this, but that's the state of it.
Final question, comment. Carlos, you wanted? No? Yes.
Probably a very naive one. When the data came out, they usually quote the shear mass, right? And they are apparently, even using these nonlinear models, they are able to provide a measurement of the mass. I guess the redshift, I'm not sure how the redshift, where they get the amplitude providing the
That's a wonderful question. So I didn't mention it because I didn't deal with that. So we don't measure masses. We always measure redshifted masses. Because you see, all that we did, if you take the black hole and the black hole system, the center of mass of your system, and you just boost it, you're going to get exactly the same equations, except that instead of m, you're going to have some redshifted guy. Mm-hmm. So we always measure a combination between redshift and masses. To actually know how the masses look in the source frame, you need to know something else about the galaxy where this guy lives. Or
So do frequencies get a stretch because of the cosmological expansion?
Yeah.
Do they get redshifted as any other physical?
Yeah.
Okay. And second part of the question is, you said that those frequencies depend on m, the mass, and a, the angular momentum, right? The spin or the...
Right.
Why do they, from the little that I know from the papers, they never quote any spin for the black holes. So they are able to estimate the shear mass, but they never said, look, we knew that these two guys were spinning. Do they measure A too as well for this?
They measure A, so the spin is always a subdominant effect if you look at the contribution. So of course the bounds on the spin are much weaker. And it happens, actually I think that's something for all of us to think. It happens that all of the events that we've seen so far seem to have an extremely low spin for the individual components. I don't think we understand why. Of course, it's either related to formation mechanisms or some exotic physics going on. But the reason is, they do quote, you find bounds on the spin of the individual components, but it's just very small.
Thank you. Okay, so unless there are questions, let's thank Peter for this great lecture again. So we're saying that we only have, today we have a short coffee, otherwise we're...
20 past 11, so let's do it 20 minutes.
So shall we have 20 minutes coffee, right? Otherwise we're going to run too late into the...